Hi, our group is DJ Easy. I'm Suing. The blue sugar is Angeline, and the white sugar is Chuckit.
We are going to present the logical circuit for our system, which is automated machine diagnostic and protection system. So we are going to show two types of logical circuit configurations for our system. The first type is gate level configurations. These configurations will only use basic gates. So including the AND gate, OR gate, and the NOT gate. The other type is NAND configurations. This configuration uses only NAND gate and NOT gate. So the system has four inputs, which labeled as IRCT. Then we move to the output. We have three outputs for our system, which labeled as AWM. And now I will pass to Angeline to explain how we created our logical circuit using Quartus.
Thanks, Wayne. So to create our logical circuit using gate level configuration, we base it on the minimum expression derived from the K-map on the right side of the screen. So for example, we want to show how to connect input to the output gate to output A. We look at the minimum expression on the right side, where A equals to I bar or R bar or R and C bar. So we look back on our quarters. How we do this is by first, if we want to get I bar, we first have to connect the I input to the NOT gate, and then to get R bar, we connect R to the NOT gate, and then to get R and C, we connect a C bar. We first get a C bar by connecting C to the NOT gate. And by combining all these three using the OR gate. And finally, connect it to the output. So this is our final look of the logical circuit using gate level configuration. So now I'll explain how do we convert from basic gates to NAND gates. So if you look to the right side of the screen, to convert, there are two basic gates that we need to convert in this circuit, which is OR gate and the AND gate. The method that we use to convert it is pushing bubble method. So to convert the OR gate, we first have to add two bubbles on the input side of the OR gate. Then we push the bubble towards the input. So for I, it will become an inverter. R, it will become an inverter, and one of the bubbles will connect to N. So this will form a NAND gate. And then as for the OR gate with one bubble on one side, it will become the NAND gate. And how we convert an AND gate is just by putting two NAND gates, because the bubble represents the bar. So when you have two bars, it will cancel each other out. So this is the final result of how our NAND gate looks like. So now I'll pass to Tiati to explain our waveform simulation result.
All right, let's look at the waveform that we simulated in Quartus. If the line is at the bottom, it represents logic 0. On the other hand, if the line is on the top like this, it represents logic 1. Since the output is simulated by the SOP expressions, we have expressed it by the truth table and also the K-maps. So the result will be the same with the truth table and also K-maps. But why? There are many don't cares in the truth table that you can see and also the K-maps. But there are no any don't care in our waveform. This situation can explain like this. If the don't care is loop, when we express it as a expression, we will consider it as logic 1. For example, we can look at the input combination 0, 0, 0, 0. In the K-maps, the output A of this input combination is equal to don't care. So the expressions, we loop them to get the bigger loop for simplified our expression. So if we loop them, so it will be considered as logic 1 in our waveform. On the other hand, we can look for the example implementation 1, 1, 1, 0. In this case, the infinite combination will be considered as don't care too, but we don't look it in our SOP expression, so it will be the logic 0. Okay, let's look at our waveform. 1, 1, 1, 1, 0. Okay, this is clearly we can see that the output A of this infinite combination is 0. To conclude that, since the gate level configuration and NAND configuration have the same SOP expression, so that of course the waveform simulated will be the same.